Welcome to Breadboarding. This is video 29 in the Breadboard 8088 PC series, PC Compatibility Part 7, and we're going to be looking at initially configuring the DMA controllers, and then in the next video after this, video 30 Part 8, we'll be looking at the floppy disk controller. So in our high-level plan, we're working towards building a basic floppy disk PC able to boot an early version of MS-DOS, and really the last two steps in this is configuring the DMA controller and wiring that in that we've already installed some of the chips for the DMA controller already, but not all of it's been wired up properly, and then designing a floppy disk controller and installing that. So what is DMA? So DMA stands for Direct Memory Access, and this is dedicated hardware for the transferring of bytes of data between memory and peripherals such as floppy and hard disk drives. Now the Intel 8237 DMA controller, which was used in the original PC PCXT, is relatively limited. It's only capable of doing 64K chunks of RAM at a time and only has the ability to drive 16 address lines. In later versions of PC, certainly from 486 upwards, where there were chipsets, then the DMA controller would often be emulated actually in the chipset. And the fact that a modern computer can still boot to MS-DOS and use DMA would indicate that even modern PCs still are backwardly compatible. It's also worthwhile mentioning that the DMA that we have for the PCXT ISA-bus is different from PCI Express DMA, so we don't need to get confused with that. Now, it's quite a good book which is available online at the URL here, which I'll include in the description below the video, and it's worthwhile having a quick look at that. This is available from the URL I gave you. It provides quite detailed descriptions of what's going on for all of these things. And in fact, the DMA section is quite useful in that it also includes this bit here, which actually says this is how many clock cycles it would take to transfer a byte of data between an I/O peripheral and memory. So with the 8088 processor, this would be about 39 clock cycles. And if we then look a little bit further down, and then down here it actually explains that if we're using DMA, then it's probably about 10 clock cycles. So this section in here is quite useful if you want to know more about how DMA works. I've also referenced this section here which explains how the register which is used for doing the A19 to A16 address lines and how this is accessed, in particular using the DAC2 and DAC3 signals. So this is just summary. So we can see here the DMA should be about 4 times faster than the equivalent 8088 instructions, and the calculation provided in the book indicates that the 4.77 megahertz XT should be capable of about 476k per second over DMA. So we'll perhaps have a look at this in later videos to see what the actual throughput rate is. So this is the overall system diagram that we reviewed in some of the earlier videos, and you can see here that we've got the main data bus and there was also the X bus, next data bus. Now, as we discussed in earlier videos, we're not going to bother with the X bus in this particular case. I think it was largely needed because the drivers for the bus here wouldn't be capable of doing all of the 8 ISA bus slots plus all the other chips here. However, because we can control this a little bit better on our breadboard PC, then we're actually going to eliminate the bits of the buffers that were needed to support the X bus, and all this lot is just being connected up. So if we have a look at the DMA controller, there is a DMA address latch because the DMA controller only has pins for the lower 8 address lines, and so it needs to latch the data bus onto this address latch here to do the upper 8 address lines. And then because the DMA controller can only directly access 64K of memory, we actually need this page register to handle the top 4 address lines. So this is the DMA controller diagram that we looked at in some of the earlier videos. So we can see at the top here, these are the address lines for A0 to A8. Now we don't have A8 to A15 here, and we'll see the reason why in a minute. We've got the DMA request 0 to 3 lines, which this is how a device requests to do DMA. The DMA acknowledge 0 to 3, and we'll see why 2 and 3 are in orange in a minute. And then we've got various other control signals here that we'll be looking at. So ready to DMA, the DMA clock, hold A, reset, etc. are control signals we need there. Now, because not using the X bus, we don't have to worry about that U12 chip there. But the other 2 chips we do need is there is a latch for the A8 to A15 address lines, and then we also have this 4-bit wide and 4 locations register which provides the top 4 address lines for the various DMA requests. Now I should say that DMA request 0 was used originally on the original PCXT for dynamic RAM refresh, which we don't need to use for this particular design, and so we'll be ignoring the DMA request 0 line for the moment. And this is a section of the book that I've reproduced in here just to highlight that the read address A and B lines here are actually driven off the DAC2 and DAC3 lines, and the DAC is normally active low, and what this basically means is that when channel 1 is active, then both DAC2 and DAC3 are high, and therefore we'll be getting the value from the third address there. When channel 3 is active, then DAC3 will be low, and we'll be getting it from the location 2. When channel 2 is active, then we'll be getting it from location 1, and we'll never have the 0-0 condition for RA and RB because one of these will at least always be 1. So this was a little confusing when first looking at this. It basically means for the dynamic RAM refresh, then they'll never access the 0-0 values there. This is the control and clock logic that we looked in earlier videos, particularly when we're doing the wait states for I/O. So we've actually done the bits in green up here. We have actually implemented most of the circuit here in purple, but there was one difference that I have worked out, that the DMA AEN I thought was originally only used by the X bus, so we didn't need to use it, but it is actually in fact used to enable signals on the register and the address latch chips as well, so I've had to re-enable that. And then this is the XI8088 diagram that we were working from. Again, what we're going to be looking at here is we've done most of the bits in green, and this DMA controller and page register, we've already installed the 3 chips. So there's the DMA controller, the address latch, and the 4-bit by 4 register stroke. It's effectively dual port RAM, in fact, because we can read and write to the RAM at the same time. So let's take a look at the schematic diagram for the breadboard PC. So I've updated the diagram, and if you remember last time, we've got the processor down here, we've got our video card over here, we added the keyboard controller over here in the previous video, and what we're going to be doing now is configuring the DMA controller, which is here, the address latch for the A8 to A15 lines here, and there's also the register that is doing the top DMA address lines for A16 to A19. And in earlier videos what we have done is configured a PLD here for implementing the clock and wait state circuit, and there are a number of signals on here that weren't hooked up to the DMA controller, which I've now done that. So now basically all the outputs from here are now connected to the DMA controller. So if we go in and have a little bit more detailed look at the DMA controller and what the various pins and signals are doing here. So we have the request lines coming in here, so DMA request. So DMA request 2 is in fact going to be going to the floppy disk controller. I don't believe there's any others we're currently using at the moment. If we have a hard disk controller at some point in time, we might use DMA 3 for that. You can see that we've got the data bus down the bottom. We've got the lower 8 bits, the address bus. So this is both reading and writing. So when the DMA controller has control of the bus, then in fact these will be outputs. But under normal circumstances, when we're not in DMA mode, then these will be inputs. We've got our normal control signals over here. And then the ready, hold A control signals coming from the clock circuit that we had over on the right hand side here. The HRQ DMA is basically when the DMA controller, as a result of the request signals coming in over here, actually makes a request to do DMA, and this goes off to the clock circuit and is used to drive the various signals that come out of here, then go to the bus controller and the clock controller. Then we've got the chip select. The DMA clock was something we talked about in some of the earlier videos. Key thing about the DMA clock is it's at the same frequency as the main CPU clock, but there's a requirement for the DMA clock to have closer to a 50-50 duty cycle, whereas a normal CPU clock is a 3367 duty cycle. And if we see here, we can see this clock circuit was generating the DMA clock that we've already done in earlier videos. Now the main issue with the DMA controller is that either the CPU or the DMA controller can control the data address and control bus. And so one of the key things we do need to make sure is that the address enable board signal here is used to actually control the various latches and things that we have coming out of the CPU here. So you can see that this control signal here controls the address buffers and latches down here, and also goes into the bus controller here, and as a result of that then this will either make all of these outputs 3-state, so they'll be in high impedance, and similarly for all of these values will also be high impedance. And during that time then in fact the address bus will be controlled by the lower address lines from the DMA controller. The upper address lines, the DMA controller will actually write the data bus values to that. The address strobe latch comes out of the DMA controller and will basically take the top A8 to A15 address bits on the data bus and will actually write it to this latch, and then will go out onto the address bus. And then finally the 4-bit wide by 4 address line register here. This is used for providing the A19, A18, A17, A16. And when writing to this is driven by the A0 and A1 lines, and as we explained previously, the DAC2 and DAC3 drive the reading address lines as well. So we're first going to hook up these additional control lines, so we need to make sure the various control signals from here coming over here, and also there's a few coming down to the bottom here and to the output enables on these buffers here, which previously were just wired to ground. So just going to put in the power tied to ground and 5 volts with the chipped in first. Then we'll put in the decoupling capacitors close to the ground connections. Check those off with the diagram. So we're now going to connect the address latch for the A8 to A15 lines to the address strobe and the other control signals there coming out of the PLD. Tick those off on the diagram. Now we're going to connect the top address line register. So put in the control signals there. To write enable the address lines for the A0 and A1, then the address lines going into the A16 to A19. That's the A19. Then we're going to put the DAC2 and DAC3, which drive the reading A and reading B, and now we're just putting in the data lines to tie across to the DMA controller, D0 to D3. Check all those off. So now we're going to do the DMA controller. So there's a couple of lines that need to be tied to ground or 5 volts, so just going to put those in first. Then I put in the TC line that goes up to the PLD at the top left hand side there. Now we're going to wiring in the reset, which comes in from over on the right hand side. Then this is the chip select, and then the DMA clock, which is a special signal we did a number of videos ago for the DMA controller. So now we're going to take the DMA and hold A signals, come over here. I think we missed out on the wiring those up in the video, I'm afraid. Now we're hooking in the IO read, IO write, memory read, memory write signals. Check those off. Now we just need to do the buses. So I'm going to do the data bus and the address buses. So I've made cables specifically to do these. So these are the A8 to A15. Then we're going to do the A0 to A7. And then we're going to change the way how the data bus is connected. So we're going to hook the data bus across to the address latch there, then the DMA controller to the address latch, and then we'll wire in the rest of the I/O at the top there. So now we just need to do the rest of the bus control signals. So this is the bus controller and also all of the buffers which need to go into high impedance mode when the DMA controller's got access. So we're just wiring in the output enables there. We took the time to ground out first. Then we're just wiring in the other signal for the bus controller there. And then this is the weight coming from the DMA down into the clock circuit. Check all those off. Okay, so I've checked off on the diagram all the connections for the DMA controller, and I think I've got everything. I will have another check before I wire in the floppy disk controller. Now, to test the DMA is a little bit awkward. The easiest way to test it really is to connect the floppy disk controller and then to see if it works and to debug things through that way. So I'm going to break the video now, and in the next video what we'll be doing is looking at floppy disks and floppy disk controller and wiring that up into the board and then starting to test the floppy disk access and see whether we can boot MS-DOS and get the Breadboard PC starting DOS. So if you don't want to miss out on future videos, please hit subscribe, and if you hit like as well, it just helps to make the videos available to a wider number of people. Thanks for watching.